continuing our last problem where we were trying to calculate Cm0 of the whole aircraft, which consists of Cm0 of wing, Cm0 of tail, and we have learned how to compute them. And then we have seen also how the Cm alpha, or the stabilizing contribution of wing and tail, can be computed. And in that we have seen for this particular example, the wing was destabilizing, so Cm alpha of the wing was positive, and Cm alpha tail was negative, as tail is a stabilizing component. And then when you add up Cm alpha wing and Cm alpha tail, total gives the Cm alpha negative. That means once you put the tail with that dimension, the appropriate VH tail volume ratio, we get particular level of static stability. Also we learned that if I give a tail setting angle, in this example it was 1 degree, minus 1 degree, and for that it generates a sufficient Cm0 value, and that value we have seen what exactly it is. We have seen also Cm0 because of wing, Cm0 because of tail, and total Cm0 also we have computed. So we have learned this art, the skill, how to calculate Cm0 of the whole airplane, how to calculate Cm alpha of the whole airplane. Of course, we have not talked anything about fuselage contribution, which we will do in some session, right? But to end this, another important thing comes to our mind. Okay, I know Cm alpha of the wing, Cm alpha of the tail, let's say for the Cm alpha of the airplane. I need to know neutral point. What is the neutral point? Why it is important? Let's understand that. What is the neutral point? Neutral point is that CG location at which the aircraft becomes neutrally stable. Neutral point, how do I define again? Neutral point is that CG location at which the aircraft becomes neutrally stable. So I will use NS. When I write NS, it is to be understood, it is neutrally stable. And if I try to translate this into a mathematical definition, we say neutral point is that CG location for which dCm by d alpha equal to 0, that is neutrally stable, or equivalently I can say dCm by dCl equal to 0. Please note that in neutral point I have also used the word stick fixed. That means I am not allowing any floating of the elevator. Okay. So initially we will be talking more and more about stick fixed, and then at some point again we'll come back to stick free a little bit so that your concepts are clear. So let's focus on the stick fixed. The understanding is this: if I leave the elevator free, it has a natural tendency to float up, most cases. However, we are saying no, we will not allow that floating. If I want to go for a 5 degree, I'll take it to 5 degree and lock it. Okay. So let's come back to neutral point, and let's try to understand this from a simple example. Suppose I have got a wing, flying wing, and it has a reflex aerofoil. You could see this is a reflex aerofoil configuration. And let's say its aerodynamic center, AC. Where will be the AC for low speed? You know, you are expert by now. It will be at quarter chord point, or 25% of the chord, right? Now let us see, if I put CG somewhere here, will it be statically stable or not? That's the question. Although we know by now that whenever AC is behind CG, it gives stabilizing moment. We can always cross-check. It's better to cross-check. Suppose if I give a disturbance, some delta alpha here, I see there will be a delta CL acting here, which will give a nose-down moment about CG. That means it will try to discourage the delta alpha, or it will try to come back to its, it will have an initial tendency to come back to its original equilibrium. So we say this is a statically stable case. Okay? And from the definition point of view, if there is a positive alpha there is a delta CL, which gives you nose down moment. So I say delta CM. So you could see that because delta CM is negative, nose down is negative. So again here, dCm by dCl is less than 0, or dCm by d alpha is less than 0. So both are mathematical conditions for attributing towards static stability, right? So what is learned? That as long as aerodynamic center is behind CG for a flying wing, this will have stabilizing effect, and the flying wing will be statically stable, right? So this is the CG, and this is the AC. Now think of a situation. Suppose I start moving this towards AC of the wing. That is, I am shifting the CG from this location towards AC. That can easily be done. You can redistribute the masses here inside the flying wing, and CG can move aft. What is the meaning of that? What will happen? If CG from station 1, it comes to station 2, that means this moment arm has reduced. Okay? So the restoring moment magnitude will reduce, although sign still remains negative. So we say it is still statically stable, although the degree of stability, static stability, or the amount of static stability has reduced, because this moment term has reduced. Now imagine if I take CG further close to AC, what will happen? As long as that CG is ahead of AC of the wing for a flying wing configuration, please understand I am talking about a flying wing, there is no tail at all. So as long as AC of the wing is just behind CG of the aircraft, it will have a stabilizing effect. Natural question comes, what happens if CG and AC of the wing coincides, same point? Then what will happen? There is a moment term is 0, so there won't be any moment even if there is a force. So it will not generate any moment for any angle of attack. So that is the point where we say it doesn't have any restoring moment, and it is a state where you say the aircraft or this flying wing is neutrally stable. Now, if I try to draw, understand this through Cm versus, let's say, alpha graph. Okay, I want to draw Cm versus alpha graph for this configuration. So this is alpha equal to 0. So what is your guess? At alpha equal to 0, will there be any Cm? Look here. If it is symmetric, if it was just like this, at alpha equal to 0, definitely there is no Cm, because the forces here are equal in magnitude. They cancel each other. To be more precise, the pressure difference neutralizes, and there are no net force. So naturally, net moment will be 0. But the moment I have put a reflex aerofoil, this is reflex, you could see what will happen. Because of this portion, right, there will be a force generated even at alpha equal to 0, which will in turn give a moment like this about CG, and which is positive moment. So this tells me that at alpha equal to 0, there will be a positive pitching moment. So I can tell at alpha equal to 0, there is a positive pitching moment coefficient as long as it is a reflex aerofoil. Clear? So if I draw it, so at alpha equal to 0, there is some Cm naught. Okay? Now, what about the slope? Cm versus alpha. That I know. If I again draw it, make it a little cleaner for you to understand. Let's say, first case, this AC is at C by 4. Let's say CG is here. I call it 1. So this is CG location. Okay, please understand this is the AC which is at C by 4, and this is the one of the location of CG. So now you know, because of this, AC being behind CG or CG being ahead of AC, there will be a nose down moment. So let me erase this to be more precise so that you don't get mixed up. So let me draw it. This is C by 4. So since CG is ahead of AC, for any disturbance, there will be a nose-down moment about CG, so Cm will be negative. So I know that now the slope between Cm versus alpha will be negative in this case, right? So let's say this is the Cm versus alpha slope for Cg1. Okay? Now what I do, I put the Cg little closer towards the AC. So let's say I put it here, number 2. What will happen? Will the slope become positive? No, because still there is a moment arm which will give force, which will give moment because of the force here. So again the nose down moment will come. So slope will still remain negative, but magnitude will reduce because moment arm has reduced. Now I take it to a point number 3, further close to AC. Now you know the moment arm has further reduced. So although moment arm has reduced, but still the AC is behind CG, so there will be a negative moment. So it may look like this, say 3. So this tells you or tells us that if this CG coincides with AC of the wing, then there won't be any slope or there won't be any change because of alpha. So what will happen? That this line will become something like this. This is xCg at which dCm by d alpha equal to 0, and this xCg location is nothing but our x neutral point. Correct? So what is the neutral point for a flying wing? For a flying wing, the aerodynamic center itself becomes the neutral point of the flying wing. Is it clear? Okay. Why it is neutral point? Because if I bring CG close, CG just coinciding with AC, then it will have Cm alpha equal to 0 or dCm by dCl will be equal to 0. What happens if CG goes further aft? If CG comes here, CG4 location. Now what will happen? Now the AC of the wing is ahead of CG. Suppose some disturbance is there. This delta CL will give a nose-up moment, right? Nose-up moment. So it will not have any initial tendency to come back to equilibrium. So we will say this is a statically unstable case. It is a statically unstable case. And in that case, the slope is positive because now Cm is positive for alpha. So the line will look like this. This is xCg4 location. This is statically unstable. And these are all statically stable. And this is neutrally stable. So why it is important? If you are designing a flying wing, you must ensure that the AC of the wing is always behind CG of the airplane, right? To have some static stability. But at this point, I must also tell you that unstable doesn't mean uncontrollable. You can still fly an unstable airplane by using all controllers and flight control system. In a simplistic way, if I take a stick on my finger, it is statically unstable, but still I can control. So what we say, unstable doesn't mean uncontrollable. In fact, you'll find most of the fighter airplanes, to increase their maneuverability, we make them statically stable, but marginally. Okay? So this is the understanding of a neutral point in a simplistic manner. How do I extend this understanding to aircraft? Let us see. Let's see, this is the aircraft. Let's say this is the AC of the wing. For time being, assume fuselage effect is 0. Okay? We are neglecting fuselage effect for time being, let's say. Now, if the configuration is like this, and if CG of the airplane is somewhere here, what is your answer? Whether this configuration is statically stable or not? It doesn't have any tail, please understand. It doesn't have any horizontal tail, as per diagram it goes. But the answer is very simple. You know that the AC of the wing is behind CG, so the wing will be giving stabilizing component, and so the dCm by d alpha will be less than 0. Since we are neglecting fuselage effect, So we are saying this is a statically stable case. Okay. Now, suppose I change the CG. Let's say CG is here. Or let me further make it simpler to you so that you can understand clearly. Let's say CG of the airplane is coinciding with aerodynamic center of the wing. I repeat, we are not considering fuselage effect at all. So in this case, what will happen? The aircraft will be neutrally stable, right? Okay. And if I further bring the CG aft of AC of the wing, it will become statically unstable. This much you have understood. But now let us see what happens if I put a horizontal tail here. Now the moment I put a horizontal tail there, and even if CG is coinciding with AC, do you think it will be statically unstable or statically neutrally stable? You say, okay, CG of the airplane and AC of the wing are same point. What is your answer? Please see here. Let us see this case. If CG of the aircraft and AC of the wing are at same point, when tail was not there, we realize it is a neutral stable case, right? So it will not generate any Cm for alpha. So dCm by d alpha will be 0. But the moment I put a tail here, even if AC of the wing is at CG of the aircraft, if I produce some disturbance delta alpha, and roughly delta alpha also will be here, if I neglect downwards and all, even if this is not giving any moment about CG, but remember here, there will be a delta CL tail, which will give a nose down moment, nose down pitching moment. So we are writing Cm. So this will make the whole configuration again having dCm by d alpha less than 0. Is it clear? So that is the beauty of keeping a tail. So what is actually happening? Earlier, when tail was not there, you have a limit that you cannot put the CG beyond AC of the wing. Otherwise, it will become statically unstable. But the moment you have put tail, you can easily, to some extent, to some degree, you can put CG behind AC of the wing also. Because this man, the tail will take care of the restoring moment. What will happen? Suppose this is the CG of the aircraft. This is the AC of the wing. And here, AC of the tail. So even if there is a disturbance delta alpha, there will be delta CL because of wing. Remember, CL is supposed to be perpendicular to the velocity vector, but for a small angle, I'm just drawing it like this. Ideally, it should be perpendicular to velocity vector, right? The similar delta alpha here also will give a delta CL tail, right? This man, this wing contribution will generate what type of moment? Stabilizing or destabilizing? Check here, AC of the wing is ahead of CG, so this will give a destabilizing. What about tail? Tail will give stabilizing. So now, even if the AC of the wing is ahead of CG, if you put an appropriate tail, you can make this whole configuration having a dCm by alpha, d alpha, or dCm by dCl appropriately negative. And that is what the problem, what we solved, was telling us, right? And most of the cambered aerofoil aircraft will find the AC of the wing is ahead of CG because we have seen by putting AC of the wing ahead of CG, I can reduce the Cm0 negative effect of the wing because of CMAC. Okay? So this is the understanding. So we'll now try to calculate neutral point for the given problem, and it's very straightforward when you understand this. If I write the formula for neutral point, that was x AC of the wing by C, let me write this, plus neta VH CL alpha tail by CL alpha wing, 1 minus d epsilon by d alpha. We have neglected fuselage effect altogether here. So if I put this number I should get this value around 0.5. So simple. So once you get xnp by c, which is xnp bar, which is equal to xnp by c equal to 0.5. So what is the meaning? How to interpret this as a designer? Let's that be very, very clear. So let me draw the airplane. Here the airplane. Here is the tail. Here is the wing. Of course, this tail is having some negative setting angle. So this take 1 degree. So I will draw it something like this, tail. And if this is a line, if CG is here, the neutral point is coming at around 0.5, C or C bar. And the meaning is, if I fly this airplane, I'll be able to generate Cm naught positive, and the slope at trim dCm by d alpha will be negative. That tells me clearly I can trim this statically stable airplane at a positive angle of attack alpha. Okay, because I could make Cm naught positive. Okay, so this was the problem. I wanted to clarify you few things, whatever we have derived by expression, and sometimes we get lost into all the expressions, dCm by d alpha, dCm by dCl, whatnot. But if you understand the physics, understand the skill part of it, you can easily translate this expression to your advantage, and you can design a good aircraft. Before I take this lecture, I'd like to tell you one thing, that when we do some sort of recording, and when I again see it myself, there may be some section which I would like to repeat. And my friend who are doing the recording, they say, "Sir, please come with the same shirt, same jacket, because otherwise it will look different." And I contest them, that is not possible. Okay? And our continuity is not through our looks or which jacket I am putting on. Our continuity is through the subject, the concepts, which we are trying to reinforce by repeating many times many things we have seen. So please bear with me. Sometime you will find there will be a discontinuity if you try to focus through my uniform I am wearing, because for simple reason that I am recording it at some other time. Okay? I am sure, young man and young girls, you will appreciate it. Let us come back to academics. We have been talking about dCm by dCl. And you know by now, you must be expert by now, this is Cm, this is Cl, and dCm by dCl is the slope, that is slope at the trim. And if it is negative, then you say it is statically stable. We always talk about the slope at the trim because we are trying to check static stability by disturbing the airplane at trim, at equilibrium, right? So we talk about slope here. That is more important. And we have seen this whole aircraft dCm by dCl, we have broken into dCm by dCl of wing, and then we say dCm by dCl contribution because of tail, and then plus dCm by dCl contribution because of fuselage. Similarly, there is an engine, you have seen that also affects the stability. So in some form, dCm by dCl from the engine contribution also will be there. But we have not talked about how to calculate dCm by dCl of fuselage. And today, in 10 minutes, we will be covering that. But before I cover, I'll be giving a rough idea how to calculate. But these things are generally computed through using CFD, computational fluid dynamics, more importantly through internal testing, because fuselage shapes are very of variety, having a variety contours, and there are so many attachments, so very difficult to compute it through analytical methods. However, you as a designer need to have an art to get a quick estimate of this. And you can do that quick estimation provided you understand the physics behind it. What is the physics behind it? Let's say this is the fuselage. Typically, fuselage shape will be like this, right? Here our friend, honorable pilot, will be here. Now, If I try to visualize it through most of the configuration which we have been exposed to in aerodynamics, this sort of a shape, it could be ogival shape, it could be conical shape, and the central portion I can think of a cylinder, and the later part which I can think of as if a bow tail. You know why this diameter is kept smaller than main diameter or maximum diameter, and that is we call this ratio to this ratio here, diameter at the base and diameter at where the bow tailing is starting. The ratio, if I take the ratio, is less than 1, that is to say this is less than this. And we try to see that this angle is around less than 7 to 9 degrees in normal case. Otherwise, flow will separate here. So this is typically a bow tail, right? What happens? What we are trying to find out? We are trying to find out if there is an angle alpha, right? How much this is going to generate a force and how much this will contribute towards moment about CG. One thing is very clear, if I break this fuselage into these three shapes, one thing I am pretty sure, this is the most lifting surface or lifting part of the fuselage. Right? This is cylinder, so at small angle of attack I can say, and this will not really contribute to any lift. And there, this is the portion, the bow tail, which is opposite of the nose. So this will, for a nose, if for positive alpha, I am getting a force something like this. For a bow tail, since it's reverse, you will find this will act downward. Right? So now can you tell me, if I now draw the force here downward and CG is somewhere here, you could see this, for a positive alpha, this will give a nose up moment. So nose is destabilizing. This is destabilizing because for stabilizing effect, I want for a positive alpha, there should be nose down moment. But here for positive alpha, it is giving nose up moment. Now for bow tail, even for positive alpha, you could see since it's a bow tailing like this, the force will act downward. This also will give a destabilizing effect. Okay? So what we are getting, both nose and bow tail will give Cm positive for positive alpha. So this is destabilizing. And the moment it is destabilizing, we know that for destabilizing, immediately I know Cm alpha will be greater than 0 because for stability, Cm alpha is less than 0, right? So Cm alpha, because of fuselage, will be greater than 0 or it will be destabilizing. There are methods, empirical methods to calculate the value of Cm alpha or dCm by dCl through quick formula, and that I will be giving you, and you should be using it as and when required. First of all, if this is the nose of the fuselage, and this is, let's say, total fuselage length, then this is the length of the fuselage. I will consider it from here, length of the fuselage, LF. I am not taking any bow tail effect. I am assuming the cylinder straight. Then you will see that CL alpha of the nose, this portion is nose. For small alpha, it can be approximated as 2 into some what you call Monk factor, K2, K1. And typically K2, K1, which is a Monk factor. These are for your information. I will not be able to add a lot of physics at this part of the lecture. This typical value is between 0.85 to 0.99 or 98 for L by D greater than 4. If the length to diameter, this is a diameter, if the length, total length, the fuselage and this nose included, if L by D is more than 4, then it is fair enough to take K2, K1 as 0.9. So CL alpha of the fuselage, you will get around 1.8 per radian. For subsonic case, you will find that many of the book or many of the designers take it as 2 per radian. Okay? But one catch is there. CL alpha fuselage is 1.8 per radian. And as I told you, approximately people take it as 2 per radian for initial estimates. But then the catch point is, it is based on reference area is pi d max square by 4. This should be very clear. So when you are trying to combine this with other components because of wing and tail, you have to convert this into reference area, which is wing reference area. So CL alpha fuselage will be, say, 2 into pi d max square by 4 and divided by reference area wing area. So this value you will be actually using for your all equations, right? So 2 into whatever the ratio comes, that is the CL alpha per radian based on wing reference area. This is very important, per radian, right? Okay. We may like to solve a problem, but this is not very important. You should know this, that's all, right? And then there is another expression, which is dCm by dCl for fuselage. For fuselage, this empirical formula is given, which is K WF square LF by SW CL alpha wing. I'll explain you what is LF. LF is overall fuselage length, right? WF is the maximum width of fuselage, and SW, the K part is an arbitrary constant, which is also called empirical factor, that you can find out referring a standard design chart. Just I'll give you some typical values. This may be around 0.05. This one, and say 0.05, 0.02, and these are given as 10, 20, 30, 40. Location of C by 4 of wing in percentage of fuselage length or body length, percentage of body length. That is where exactly it is located. The C by 4 of the wing. If this is the wing, and let's say this is the C by 4 of the wing, how that is located in terms of percentage of body length, that is, this location is at what percentage of the body length. If you have this number, you will get the value of K. Typically, K value you can, for all practical purpose, you can take 0.03, that will work. You will get some realistic number that may not be very accurate. Okay, you understand the fuselage is not a clean fuselage the way I have drawn it. Okay, there will be nacelle, there will be engine intake, there will be landing gears downstairs, so many things, right? There will be pods. So it is better that one goes for a scaled down wind tunnel testing and get these values. Similar will be for the CM0 fuselage also, right? So this I thought I'll give you some background so that you can understand what sort of a value of CM alpha for fuselage would be, or dCm by dCl for fuselage would be. And if not that, you should be very, very sure that fuselage will be always contributing toward destabilization. That is, the CM alpha or dCm by dCl will be greater than 0. You could see here, dCm by dCl is given like this, and this is greater than 0. That, as a fundamental understanding, it should be clear to your mind. Thank you.